Let's talk about how we handle an average for a data set, and then we're going to move into how would we calculate an average if we knew the entire distribution. Here's what it looks like when we do an average. You sum up all the data points, divide by how many there are. We could rewrite this as 1/5 times each of these values. That's sort of like saying each of these data points gets 1/5 of the weight. This is one of 5 data points, so it has 1/5 the weight of the others, except the red marker really doesn't show up well, does it? There, now you can see with the green isn't showing up any better. All right, so the 7 has 2 of the blue 1/5, as if to say 7 happened twice as often, so it gets 2/5 weight. Well, that's the way we treat data because all the data points are equally important or valuable. So let's talk about a scenario where we know all the values that X could be, and for the whole population, what those probability values are. I've left off this one, and I was about to fill it in because I was just making up numbers, but these probabilities all need to add up to 100% because these are all the possible X values. So I think these others add up to 92%, so I need 0.08 right here so that it adds up to 100%. This is the whole distribution. Let's pretend you can't be less than 1 or more than 8, and you can't be any numbers in between. How would we find an average? We're going to use the same idea we did here. I'm going to take each of the numbers times its weight, 0.02 times 1, 0.05 times 2, for all the values in my entire set. And what do I get? 5.81. That's not X bar because that's not an average from a bunch of data. It's actually the mu because this is the entire probability distribution for all the data. In fact, this guy right here, which goes by lowercase f of x, is called the probability density function, or PDF. This is where is the denseness. 7, for example, right here is pretty dense. It shows up a lot. That was in the data, which I made up. But here in our PDF, it shows that 7 should be showing up a lot, and that caused the average to go a little closer towards the 7. So this mu is also sometimes called the expected value of x. In other words, if you were to randomly generate a number from this distribution, we would expect it to be pretty close to 5.81. That's on average. If we were talking about the mode, well, which one is most likely? This one has the highest probability. We can do mode. What if we wanted to talk about median? Median is going to be where does it add up to 50%? Well, 2% here. This would take us up to 7%. This takes us up to 17%. Okay, you try adding up a bunch of small numbers when the camera's on you, okay? It's tough. So I wrote them down to help me keep track. 2%, 7, 17, 22. Where do we finally hit 50%? Here it wasn't enough, and at 7 it went way over. So the median is going to be somewhere inside 7. So in this example, 7 ended up being the mode because it had the highest probability. It also ended up being the median because that's where the probability finally went over 50%. This idea of making a separate row to talk about adding up the probabilities is actually pretty useful. Useful enough that there's a notation for it, capital F. The name we call it is the CDF, cumulative density function. So PDFs have probabilities, and the CDF has a cumulative, meaning added up probabilities. Lowercase for the probabilities, capital F for when we're talking about adding them up. Let me show you an example of how this is useful. What's the probability of x being less than 4? Well, on the table, that means x could be 3, 2, or 1, and normally I would have to add these up. But now I don't. I just say, oh, less than 4, that's the 0.17. If I'm looking for the probability of x being exactly a number, well, then I'm not going to want the capital F of x here. I'm going to come up here to the lowercase f of x. That's 10% is the probability of being 3. But if I want a range, what's the probability of being equal to 6 or more? Well, that means not 5 or less, so not the 0.32. 1 minus that 0.32 gives me a 0.68. So I can save you a little bit of work there. So now we've got ourselves some of our first tools for how do we handle probabilities in a discrete table.